Hello everyone, my name is Alexander Reeves and I'm currently a PhD student at ETH Zurich. And I'd first like to say thank you very much to the organisers of this conference for giving me the opportunity to record this talk for you today. So in this talk I'm going to be discussing some of the work that I've been doing in the first part of my PhD, and this is alongside my supervisor, Professor Alexandre Frigier, and also Professor Andrina Nicola. So the talk has this rather long name, Probe Combination Framework Pipeline and Neutrino Mass Forecast. But I hope that at the end of this talk, you'll be convinced that combined probes are very powerful techniques in cosmology and will allow us to derive strong and robust to systematic constraints from our current datasets, and also that these sort of analyses are becoming increasingly computationally feasible with modern software techniques. And I'll just mention quickly that this talk is based on a paper that we put out last year, and also a paper that we're currently working on that should be out in the next month or so. So I said that this talk was all about combined probes, so which probes are we actually talking about? Well, first and foremost, one of the probes in the pipeline is the CMB. So this is light that was emitted 100,000 years after the Big Bang, and it probes the radiation perturbation at early times. And we can measure the temperature anisotropy of this light and also the polarization anisotropy of this light, and they give us slightly different information content as they're due to different physical processes. The next probe that I want to talk about is the galaxy clustering, so spectroscopic galaxy clustering. So here we take a telescope and we make a measurement of the positions of millions of galaxies in angular space, but also when we're using specifically spectroscopic galaxy clustering, we also take a spectra for each of the galaxies in the survey using a spectrometer, and that allows us to get a good measurement of their position in redshift space, so we can build up this 3D map of galaxies, as shown here for the BOSS survey. So the main difficulty here is the modeling, so galaxies are biased traces of the underlying dark matter distribution, and so we have to model the connection between the dark matter and the positions of galaxies, and I'll come on to how we do that in this pipeline in a few slides' time. Finally, we also have weak lensing. So there's two types of weak lensing that we have in this pipeline. There's galaxy weak lensing, where we look at the correlation of galaxy shapes, and galaxy shapes can become correlated due to weak gravitational lensing of the light from the galaxies, which passes through the same dark matter distribution. And so by carefully measuring the correlation in these galaxy shapes, we can build up a picture about what the unseen dark matter distribution is between us and the source galaxies. The same physical effect also happens for the CMB, so the CMB photons are also weakly lensed, and by carefully measuring the impact of this on the non-Gaussian signature of the CMB correlations, so the quadratic estimator, we can again build up a picture about the dark matter distribution integrated all the way back to the surface of glass scattering where the CMB is emitted. So I've put all of these probes in a schematic cartoon here. On the right hand side you have the CMB, and this grey mesh represents the dark matter distribution, which is traced by these galaxies here in the foreground. And the point that I want to make with this plot is that all of these different probes will be correlated to each other in some way. And that's because they each pass through the light cone of dark matter on their way to our telescopes. So as a quick example, let's take the CMB. So the photons move through this dark matter distribution, and if there are some late time evolving potentials, so due to dark energy domination, you get what's known as the late ISW effect, which changes the temperature perturbations of the CMB photons. And these potentials are also traced by our foreground galaxies, so the galaxy clustering probe or the weak lensing probe, which measures the dark matter distribution. And so there'll be a cross-correlation between the CMB temperature anisotropies and these large-scale structure probes. And these are exactly the sort of cross-correlations that we want to pick up and measure in this project. Okay, so let's quickly talk about the motivations for combining different probes together. So as you might know, the primary motivation, or one of the primary motivations, is that you can break degeneracies by adding different probes together. And the point here is that different probes are sensitive to different physical processes, and this means that they're sensitive to the parameters of our underlying cosmological models in different ways. And that means that when we combine them, we can break these degeneracies and derive strong constraints. I'm showing an example here on the right-hand side for a combination of KIDS 1000 and Planck CMB lensing. And you can see that for KIDS and Planck CMB lensing, they have slightly different degeneracy directions in the sigma 8 omega m plane. So when we combine them together, we get these strong constraints in orange. A slightly different, but just as important, reason to look at cross-correlations and combined probes is that cross-correlations can allow us to identify systematics that do not correlate between different data sets and calibrate these systematic effects using nuisance parameters, so calibrate the nuisance parameters describing these systematic effects. Finally, by putting all of the probes in the same footing, we're in a good place to test the consistency between different probes. So if we put them all in a consistent pipeline, then we can actually robustly measure the tensions between different data sets, which is something that we're especially interested in this current iteration of the work. So what are the key challenges involved in performing a combined probes analysis? So one of the main drawbacks of combined probes is that it just ends up complicating the analysis quite a lot because you have to include a lot of different data sets and modeling in your analysis. So in particular, your data vector size grows rapidly and your covariance matrix size grows rapidly, and this can lead to numerical issues where there's numerical issues related to the instability of inverting that large covariance matrix. And each of the different probes will have their own idiosyncratic modeling, so they'll each come with their own set of nuisance parameters, and this can blow up your parameter space and increasingly complexify your modeling of all of these different probes in a joint analysis. Finally, related to what I was saying before, there can be tensions between data sets, and there's a statistical question of whether it's okay to actually combine different data sets if they are in tension with each other. I'm showing an example here on the right-hand side. So we have various different 3x2 point constraints, and then in gray we have the Planck constraints. And you can see that, for example, combining the blue and the gray would probably not be a good idea because they're quite strongly in tension. You'll end up with some constraints somewhere in the middle of these two, which is actually a bad fit to both of those sets of data. So we also need to carefully measure and come up with some metrics for consistency before we combine data sets together. So how do we mitigate this, and how do we approach this problem? So this work is based on a series of previous works where we've built pipelines for integrating several probes at the 2-point level. And the main sort of underlying idea behind these frameworks is to restrict to scales and summary statistics, so just 2-point statistics, where we can simply model the data and model the covariance matrices. So in particular, we try to stick to linear scales far away from any scales where baryonic feedback might become an issue, and we try to keep the number of nuisance parameters small to not blow up the parameter space. So the idea is that we win by adding lots of different data sets together and not necessarily by extracting all of the possible information in any one given data set. And as I said before, we can use these cross-correlations to help calibrate our systematics, and we'll see an example of that in a little bit. And finally, to make this all computationally feasible, we need to have a quick pipeline, and to do that, we have written everything in JAX and built emulators for our theory predictions such that the whole pipeline is differentiable and can be JIT compiled to make everything very rapid. So here is a quick schematic overview of the pipeline. It's quite a busy plot, but I'll just walk you through it very quickly. On the left-hand side, we have our simulation processing pipeline. So here we take N-body lightcone simulations from a suite called the CosmoGrid, which is publicly available. And we turn these into correlated mock realizations of each of the different probes in our pipeline. So here we add realistic survey noise, we add the survey masks. And from these correlated mock realizations, we can create our covariance matrix, which we end up using in our likelihood. And then on the right-hand side, we have our theory prediction framework. So here, as I said, we use JAX-based neural network emulators to speed up the inference of this pipeline. So we train emulators in JAX, and we write all of our likelihoods also in JAX. And then finally, in the middle, we have our actual survey data, and from this we derive the data vector. Then everything goes through a compression stage to reduce the size of the data vectors and make everything a bit more numerically stable. And finally, we derive our constraints. So I just want to focus in on the left-hand side of this plot and talk a bit more about the simulation processing pipeline, because this is one of the things that we released along with the paper, is a publicly available UFalcon 2 code. And what this code is designed to do is to take input N-body light cone simulations and produce signal realizations of all of these different probes. So it can produce, in particular, the ISW, CMB weak lensing, galaxy weak lensing, and galaxy clustering. So far for galaxy clustering, it's just a simple linear bias model, so we restrict our analysis eventually to scales where this is applicable. So some more advertisement for UFalcon 2. This is hosted on PyPy and has full documentation and examples, and we tested that the maps that we derive in the end are consistent with what we expect from theory, both at the 2-point level and at the 4-point level in terms of the covariance matrix. And just to mention, this has been used in several previous projects, and it's currently being used in several upcoming projects, which is exciting. So as I said, we use this pipeline to get our multi-probe covariance matrix. So we use the fiducial simulations of this CosmoGrid suite. And there's 200 of those, and we supplement them each with 10 different noise realizations and use the full suite of 2,000 maps for each probe to create this fully correlated covariance matrix. So this is just for the LSS probes. The CMB primary, so just the TT, TE, and EE, are treated separately, and we use our own likelihood for that part of the pipeline, which means that we ignore the cross-covariance between the LSS and the CMB probes. So this is already what's typically done in most analyses, and we've also checked that this is a sufficient approximation for this, for stage 3 data. Okay, so to get more specific about the paper that we put out last year, this was a forecast analysis for 12 different 2-point functions. And the main idea was to validate the pipeline, so ensure that we recover the input cosmology when we run everything end to end, and also to forecast some neutrino mass constraints. And as you'll see, we also explored some of the impacts of systematics on our neutrino mass constraints. And we make mock realizations of 3 different surveys, so Planck, so both the temperature, polarization, and the CMB lensing, BOSS, and KIDS. And you can see the sky overlap here, which means that they will have some cross-correlation between them. So firstly, forecasting the neutrino mass constraints, first thing to say is that our fiducial cosmology is always in these purple lines and stars, and you can see that we recover that in all cases. And on the left-hand side, we're looking at a case where the true neutrino mass is the minimal neutrino mass from oscillation experiments, so 0.06 electron volts. And you can see that we are adding in different data sets. So we just have all of the LSS data, just the CMB plus CMB lensing, and then the full 12 cross 2-point combination. And you can see that the information content, as you might expect, increases as you increase the number of probes in the pipeline. You can see that in this case, we get a competitive upper bound in the minimal neutrino mass scenario. In a high neutrino mass scenario, where the truth is 0.15 electron volts, we can actually make about a 3 sigma detection of the neutrino mass. Okay, so I said that we didn't just want to look at, the potential constraining power of this pipeline, but also explore the impact of systematics. And one of the systematics most pertinent to the neutrino mass in the literature has been the so-called A-lens systematic. So A-lens is a phenomenological parameter which rescales the amount of lensing power in the primary CMB anisotropies. So in the theoretical computation of the primary CMB, you change the amount of lensing. And if everything's consistent in ΛCDM, then A-lens should be 1. But actually what Planck PR3 finds in 2018 is that A-lens is greater than 1 with a confidence of about 2 sigma. And the question is, does this bias the neutrino mass constraint towards low values? And the reason it might do that is that lensing is anti-correlated with the neutrino mass, and that's because neutrino masses typically, high neutrino masses typically suppress the matter power spectrum on small scales, and this effect is anti-correlated with lensing, which requires more matter. So if you have an enormously high amount of lensing in your CMB primary power spectra, then you expect your neutrino mass to be biased low. And we're in quite a good place to explore that effect because we can just change the input cosmology with various different A lens and look at the impact on the neutrino mass constraints, and that's exactly what we do here. So here we're in the high neutrino mass scenarios, so the fiducial input neutrino mass is 0.15 electron volts. And on the left-hand side, we're just doing a CMB alone analysis, so just CMB primary, no CMB lensing. And we look at the impact of shifting this A lens parameter. And as you can see, and as we expected, as we increase the A lens, we shift the neutrino mass towards lower and lower values. And I will say that the Planck 18 central value is about 1.18, so already quite high A lens, already has quite an impact on the neutrino mass constraint. This is mitigated if you include other data sets, and that's exactly what we show on the right-hand side. So here we have the same scenario set up, but in the 12 cross 2 point case, and here we see that we can derive robust neutrino mass constraints, even in the presence of this A lens systematic. So this large-scale structure data is helping to recalibrate everything and keep the neutrino mass constraint consistent with the input cosmology. So there's more discussion of the mechanism by which that happens in the paper, but these are just the highlighted results. So this is another nice reason to do combined probes, so you can work out these internal inconsistencies and recalibrate everything. So just a quick flash up of what the current status of this A lens tension is. So as you might be aware, there was a recent Planck reanalysis with the N-pipe framework, and there's two likelihoods. There's HeliPop and CamSpec, and HeliPop basically finds a lens of 1, CamSpec finds a lens a bit bigger than 1, but nowhere near as significant as it was in PR3. And you can see already the impact on the neutrino mass constraints, that they degrade significantly compared to PR3. So it does seem like this A lens is having some effect on these neutrino masses that we derive. And that brings me nicely on to the conclusions, because that's exactly the sort of effects that we want to explore in our data analysis for the upcoming paper. So to conclude, in this work we developed a pipeline for combining many different probes using a mixture of simulations, neural networks, and survey data. So the main takeaways are that we built and validated this pipeline, and we showed that we can derive constraints, and that this is becoming computationally feasible due to modern software techniques. We can find about a 3 sigma constraint in a high neutrino mass scenario, and that mitigating systematics is a big advantage of doing a combined probes analysis. And finally, some advertisement for the upcoming paper. This will be the same analysis, but with real data and adding in a couple of different data sets, and especially these updated Planck likelihoods, and also including some ACT data. Thank you very much for listening.